Hi guys, how are we doing? Do we have anyone with us yet? Yeah, waiting. Say hi when you get on. Are we getting on okay? Happy days. Where me there? Hello Emma. Hi, is Shaq? Hello, Michelle? Michelle? Which one is it? Michelle? Is either right? Both wrong. How are you guys doing? Did you guys see the results? God, it was yesterday. Did you see the results yesterday? What did you think of them? The grade boundaries went up a little bit this year from last year. So the paper 1 was definitely probably as hard as last year, but paper 2 and 3 were definitely better. You got B in physics AS. That's good though. Or do you think, does your school give you the opportunity to repeat it next year if you want to try and get an A? Yeah. AQA has been mad recently, but at the same time, the paper's been so hard, but the grade boundaries are lower because of it. Hey Omar, you're not going to repeat it. Well, B is like a really solid start. Like you're going in with a B, and you're only going to get better, right? Because you got a whole full year of physics. Kai, your predicted is A star, AA. Awesome. It's good you got your predicted grades already. Simple harmonic motion. Did we do simple harmonic motion at the start? I know I should remember off my head what I've got planned, but I planned it like a couple of months ago. We're doing simple harmonic motion 100% at the start of year 13. So if you choose to do the full course, 100% that first month, we're spending time on simple harmonic motion. I just can't mind if I planned it for summer school. Maybe Garrett knows. He knows better than me this stuff, to be honest. Kai, what subjects are you doing these? A star, AA? I know. So summer school is free, right? Because we're trying to show you guys that it's an option. I'm going to talk in the last 5 minutes about what the full course is, like how much it is. So then you can ask me lots of questions about it then. So we'll do today's lesson and then we'll spend like 5 minutes at the end or 10 minutes at the end talking about it, sure. Math, computer science, physics, and further math. That's awesome. Just be wary though, because remember predicted grades, they're always inflated slightly, right? So if you want those grades, you still got to work hard for it, right? But I'm sure you do mad because if your teacher's already predicting grades like that, that's really good. But predicted grades can be dangerous because sometimes I think people get very comfortable with predicted grades, thinking like, oh, my teacher thinks I'm A star level. But I don't know how your school does it, but our school did it where you predict a grade that is like best case scenario. So this kid is like going to smash studying the whole year. So you always kind of pick a grade higher than where you're sitting at. So just make sure you smash it this year. Actually, Garrick, I don't. Garrick, I don't know. Did I do your prediction? I must have did your prediction grade. What did I predict you? I don't believe that I predicted anything less than an A. Wait, so what do you mean? What a turn? What an interesting turn. Sure you got. Did you not? Did you not get those grades? Or did you get an A in physics maybe? I don't mind. To be honest, yeah, but Garrick's grades, Garrick still got an A and he had a questionable year 13 experience. I wasn't his year 13 teacher. I was just his year 12 teacher. So he smashed it. Omar, you haven't had your predicted grades yet? Oh, to be fair, some schools don't get them back until the first week or first 2 weeks back to school, because sometimes, like, even though we do best case scenario, sometimes your teachers will, it still has to be realistic, right? Like if a kid's sitting on a D, I'm not going to predict an A. Best case scenario is probably a C. So like it's quite hard hitting for some people because it limits the choices of university you can make. So sometimes schools hold back until after summer so they can have like proper discussion with the whole year about how it works. Jasper the Penguin Amir. Did you mean to write that? Okay, so electric fields. So just to see what we know, can you have a go at the first one then? So we talked about this last day because we did our first, remember, we did the big intro to fields, we did gravitational fields. So the first question there is, gravitational fields are created with anything with mass, and I don't think so mass, we did last day, right? Gravitational field strength is force per unit mass. So what do we say was electric fields? Any charge, yeah, good job. So electric fields, yeah, moving current. Yeah, good job. So anything with so current is what we call moving charges. Yeah, good job. So electric fields are anytime we've got charge. So electric fields, what we're doing today is force per unit charge. Okay, so it's when we have got charges present. Remember, Q stands for charges. Okay. What's a big difference, do you think, between gravitational and electric fields? So we learned that gravitational fields are always something, but electric fields might be what? Do you know? Yeah, J and B, that's exactly what I was chatting about. Good on you. Yes, lovely. So electric fields, you know, if you got like charges repel, opposite charges attract. I think you remember doing that. So like charges repel, opposite charges attract, that's like GCSE. So we learned gravitational, remember, is always attractive. So gravitational is always attractive. Whereas electric fields, they can be both attractive and they can be repulsive. Right? Because remember, attractive is like charges, opposites attract, and then like charges repel. Yeah, so opposites attract, like charges repel. Okay, this one we just did because I just wrote it up there, sorry. Electric field strength is our force per unit charge. And then down here, how do you think, maybe you can like try to describe it in words or draw it in your work pack. How do you think the electric field would look between these two parallel plates? What direction would I draw my electric field? So for example, the other day when we had gravitational field around the Earth, we said that we can model it as uniform for the first about 100 meters, right? We model it as uniform. So how would you draw the electric field then between the two plates? Or do we remember, hopefully, what the two plates are? So hope when I learned they're positive, negative, right? Positive's got more lines in it. So the longer side is your positive and the shorter side is your negative. So all this side will be a positive plate and all this side is a negative plate. I was asking you just if you knew the direction, but the real equation for it here is that the electric field is the force per unit charge on a positive test charge. Right, so last day, remember we said gravitational field strength is force per mass, per unit mass. Today what we're saying is electric field strength is force per unit charge on a positive test charge. So remember last day we said, like if I've got the Earth and I had a little unit mass here, the gravitational field lines show us the direction that mass would move. So what we're doing with electric field lines, we're showing the direction a positive test charge would move. So for example, if I was to put a positive test charge right here, clearly it's going to get accelerated down towards that negative plate. So electric field lines, we always draw from the positive to the negative. So hopefully you can see between these two plates, we'd have a uniform field, always going from the positive down to the negative. Okay, so that's our electric field lines. So again, electric field lines are force per unit charge and always shows the direction that a positive test charge would move. Okay, so what do you think would happen then if I put an electron in here? What's it going to do? If you pop in the chat. If we put an electron in there, what would it do? So we've popped an electron in there. What would the electron do? Go towards positive plate. Nice, but Kai, yeah, that's a bit better. Yeah, attracted, curl towards positive plate is nice, but yeah, I want that word that Kai said there, accelerate it, right? Because we know that any time that we have a resultant force on something, because F equals ma, anytime there is a resultant force on something, yeah, Talish, good job, there is going to be acceleration, right? So if I place an electron here, it's going to get accelerated towards that positive plate. So we just write accelerated to the positive. Are we okay with me writing, like, so positive is plus VE, and then negative is negative VE. So positive plate. Okay. Thank you, JMB. Okay, so this one slide here should be in your work pack. It's just like kind of knowledge for you to have. So what we're saying here is every particle attracts or repels. We said that a minute ago, right? We said that electric fields can be attractive or repulsive. We did say that they showed the direction that a positive particle will be moved, and we're looking at a positive test charge. So we looked at these two plates here, and we said that if we placed any positive charge here, it's going to get accelerated towards that negative plate. So our electric field lines show us the direction that a positive charge will move. So again, our electric field strength that we represent with a capital E is found as the force per unit charge on a positive test charge, okay? So if you're doing your AQA spec, and we said they're so particular about your definitions, you can't just write force per unit charge. You say force per unit charge on a positive test charge, okay? And the units make sense because force is measured in newtons, charge is measured in coulombs, so newtons per coulomb. So we're just going to practice that today. Okay, so here I've got my two parallel plates again. It says, can we prove, using this equation as a starting point, that the electric field between the two plates is the same everywhere between the plates? So I'm asking you, can you combine some other equation with this first equation to show me that the electric field in this region is constant? Can you give it a go? So for a hint, I've got the voltages of the two plates there. So we're looking for an equation that's probably got V in it. So how do we prove that the electric field between those two plates is the constant everywhere? And give me maybe guess an equation in the chat that we're trying to combine. When we do the molar gas constant and the Boltzmann constant, Teddy's give me 2 ticks and we'll come back to that, okay? So E equals VQ, good job. Energy is voltage times charge, I would agree. And then I'm seeing a W in there, so how do we go from E equals VQ to showing that the electric field is the same everywhere between here? So maybe I'll give you a hint. Normally you're given the distance between these two plates. So what equation would you combine with this one to show that electric, yeah, good job JMB, good job, work done is force times distance. Remember, work is always measured in joules, energy is measured in joules, so those have the same base units. So we can say that force times distance equals V times Q, okay? So what we have here is force times distance of V times Q, and I want to prove that the electric field is everywhere, so I need to show that F over Q. So if I divide both sides here by Q, what we end up is FD over Q equals V, right? But I know that F over Q is E, so now I just want to have F over Q on this side. So F over Q is going to equal to V over D, and that equals our E, right? Because electric field strength is force per unit charge. So what we've proven here is that the electric field is the same everywhere between those two plates because we know the voltage between the two plates and the distance between the two plates. Okay, so this is the second equation we're going to start practice now. E equals V over D. Yeah, amazing. Okay, so just before we practice that, Talisha, I just don't want to go on too much because I don't want to confuse in the topics. But so the molar gas constants, remember there's 2 equations, PV equals nRT and PV equals nKT. You use whatever one of those 2 that you have the other information for, right? So look, both of them have PV in it, both of them have, so if you were given the number of moles in the question, you would use this one. If you were given the number of particles in the question, you would use this one. So Talisha, it just depends on what information you're given in the question. So if they give you number of moles, use the first one. If they give you the number of particles, use the second one. Because little m means moles and capital N means number of particles. Okay? Okay, so what we just said here is we said that electric field strength is force per unit charge. And we said that that's also now equal to the voltage over the distance between the plates. So can you really quickly calculate the electric field strength at X and pop in the chat? What will be the electric field strength at X and pop in the chat? Talish, I'm glad. Is it Talish? Is that how you say it? Okay, so can you calculate what the electric field strength is at X? So someone be brave and give it a first go. So we have our equations up here that we just did. Makes sense. Our electric field lines go from positive towards negative because they show us the direction that a positive test charge would move. We've got a uniform electric field in here because they're always equidistant apart. Patrol. We did, I think it was lesson 1 of summer school. So PV equals nRT. P was pressure, V was volume, capital N is number of particles. You just wrote the equation slightly wrong. K is the Boltzmann constant and T is the temperature. And then PV equals nRT is pressure times volume is number of moles times molar gas constant times temperature. Okay, thank you, Greg. Talish. Okay, question 1. JMB says 40,000 newtons per coulomb, and then we're going to write it the way that we only get marks, hopefully, in year 13. So 40,000 newtons per coulomb. Yeah, fab. Okay, so what we're saying here is electric field strength. I'm given the potential difference between the plates, right? I've got a positive 2,000 here and a negative 2,000 here. So that difference between the two plates, hopefully everyone saw the way that JMB saw there, the difference between the two plates there is 4,000. And the distance between the plates is 10 centimeters. So hopefully remember it has to be in meters for the equation to work. So it's 10 times 10 to the negative 2 meters. So when you divide those two together, you get the exact answer that JMB put in there, 40,000 newtons per coulomb, okay? Or there's a few units you could use. This one's newtons per coulomb, or if you look at it now, you could also write volts per meter. Either one is fine. So 40,000 newtons per coulomb or 40,000 volts per meter. Anyone's grand. 400. How'd you get 400? Oh, you forgot the centimeters. So just be careful with the centimeters there, yeah? So remember, it has to be, remember SI base units? The equations only work if the units are in their SI base units. So that's why I had to put in the meters. Okay, so we just found out what the electric field strength is X. What then is the electric field strength at Y? Pop in the chat. What's the electric field strength at Y? So remember we said between the parallel plates, there's some fact about the electric field strength everywhere. Yeah, Kai, thank you, good job, right? It's the exact same thing, because hopefully you can see the math. At Y, we still do the potential difference between the plates, it's still 4,000. The distance between the plates is 10 centimeters. Yeah, it's uniform, thank you. So Y is just the exact same as what it was at X. Yeah, nice. Because it's uniform here, the electric field is the same everywhere between two parallel plates, okay? So everywhere between parallel plates. So if I asked you to sketch me a graph of electric field strength against distance, hopefully because we just said that it's the same everywhere between the plates, we would find the number 40,000 for electric field strength and we just draw a straight line across because the electric field strength is the same everywhere between those parallel plates. Okay. Right, number 4 is a bit of math, see if you can figure it out. So I've given you the information there you need. So I told you what the charge of a proton is and the charge of an electron is. So it says, can you calculate the magnitude and the direction of the force on an electron placed at Y? So I'm going to put an electron right here. What is the force on it and its magnitude? It's a force on it and its magnitude. See if you can give it a go and pop in the chat. What's the force on it and what's its magnitude? So remember, we've got our equations up here. So I want to know the force on an electron placed in the field. So how do we find the force on an electron? So what we're thinking, remember, electric field strength is force per unit charge. So when I find the force, I do the electric field strength times by the charge. So we're thinking, what did we just find the electric field to be? We just find the electric field is uniform everywhere, and it's a set number of 40,000. And then think about what charge we're going to use if it's an electron. Yeah, JMB, perfect. Thank you, good job. So because it's an electron, the charge is 1.6 times 10 to the negative 19. So we just have to multiply those two numbers together. Yep, Talish, beautiful. Yes. Soham, yeah, is that how you say it too? Soham, if you want to type your name in phonetically, hopefully I'm saying it right though. Soham. Yeah, Talish, I didn't even notice you put the negative in there. They're perfect. Kai, good job, right? Because we need it to say direction. Nice, so nice that you said towards the negative plate. However, is that correct? Because it's an electron. Okay, so hopefully you type those in. We're going to get 6.4 times 10 to the negative 15 newtons, because forces are measured in newtons. And then it said we want to give the magnitude and direction. So we give the magnitude. Remember, it's an electron. So remember, opposites attract. The electrons actually go towards the positive plate. So if you look at it there, it's actually going to go towards the left, or we could say towards the positive plate. Yeah, Omar, thank you. Yeah, towards the positive plate. Soham, thank you. Talish and Soham. Yep. Okay, so 6.4 to the negative 15 towards the left. Yep, grand. Okay. Ashna, no worries. You missed a little bit of the intro, but hopefully when we go over it quite a few times, you'll be grand. Okay, so now I want you to sketch the electric field lines in these 4 situations. So hopefully you got these 4 pictures in your work pack. If you don't, just sketch them on a piece of paper you have now. But what I want to say is, how would you draw the electric field lines between these different situations? Okay, so we kind of did this one when we did the gravitational field. Remember when we did the gravitational one, we talked about a mountain and how the field lines are uniform far away from the mountain. But then if I have a mass and I place it here, it's going to be slightly attracted towards that mass. So that's quite a similar hint situation to this one. Okay, so hopefully first thing we're thinking, electric field strength is force per unit charge on a positive test charge. Okay? Yeah, yep, JB, good job. So a positive test charge, if I placed it right here, it would accelerate towards that negative, right? And move across the field line from the negative. But if I placed it right here, if I place my positive right here, clearly it's going to get repelled and move out the way. If I placed it right here, it's going to get attracted this way. If I placed it right here, it's going to get attracted this way. If I placed it right here, it's going to get repelled this way. If I placed it right here, it's going to get repelled this way. If I placed it right here, it's going to get attracted that way. If I placed it right here, it's going to get repelled from that side, but attracted to this side. So hopefully we can start to see how our field lines would look in these 2 situations. Yeah, it does, right? Because the field lines show us the way that a positive test charge would move. So that's why you have to put it in the definition. Because if we put a positive here, that's how we know the field lines are going to point outwards, because of the definition. Because that's why we push it out rather than push it in. Do you see? If we push them in, we get it wrong, because that's not what the definition is. Okay, for this one then, hopefully you're thinking, you just put your positive charges and see what happened. Put my positive charges here, it's going to get repelled from that positive charge. But it's not going to move towards that positive charge because it's also repelled. So if I put it here, again, it gets repelled. That one's quite easy. Get repelled, here it gets repelled, here it gets repelled, here it gets repelled, here it gets repelled. And then I'm thinking, is here it's going to get repelled from both sides. So that's why you say it starts to move in that curve there. So hopefully we can see that between them, we would start to get this pattern. Okay, next one then, we have to draw a field line. So again, you put your positive in places and see what's going to happen. So hopefully you're thinking, if I put a positive here, it's going to get repelled from the positive, accelerate it towards the negative. That's why the positive moves. And then put it here, repelled from positive, moves to negative. So again, that's how we can start to see how our field lines would look. On this side, if I put positive there, it's going to get repelled, positive there, repelled, positive there, repelled. Put a positive here, attracted, positive here, attracted, positive here, attracted, positive here, attracted. And this one, put a positive here, attracted, positive here, attracted. So that's why I was telling you, it's very similar to that one where we had our gravitational field lines around a mountain. So positive here, because that's more dense, there's more charge there. That's why we start to have those lines start to curve in towards that negative charge. Okay? So this does come up sometimes where they give you pictures and they ask you to pick which one is the correct way to draw the field lines. So this would be like a 1 mark towards that multiple choice section at the end. Okay, so now I get into the math. So hopefully you're starting to see that gravitational field lines and electric field lines, the topics are really similar. So it's quite helpful. So remember when we did the gravitational law, okay, we said that force equals G, the universal gravitational constant, mass 1, mass 2, over the distance between them squared. And we talked the other day about how it follows the inverse square law. The Coulomb's law is really, really similar, right? The force is proportional to the product of the charges, same way here, force was proportional to the product of their masses, and it's inversely proportional to the square of their separation. Whereas this one, again, inversely proportional to the square of their separation. So the 2 equations are really similar. The only difference is here we use a universal gravitational constant, and here we have to use 1 over 4 pi epsilon naught. And again, they found that constant just by doing loads and loads of observations to see what number works. So the number that worked is 1 over 4 pi times epsilon naught, and epsilon naught is called the permittivity of free space. It's kind of like thinking about the conductivity of free space. So that's the number we always use for E naught, okay? Okay, so clearly here we can see again, if I have Q1 and Q2, because they're opposite charges, they'll be attracted towards each other. And these forces, remember, are going to be the exact same because of Newton's third law. Opposites, the force A puts a force on object B puts an equal but opposite force on object A. Here again, these forces are going to be the exact same, but this time they're repelled. Okay, so we're just going to practice now how to use that math. Okay, so this gives you a chance to practice the math and what we've learned so far. So can you pop in the chat the answer to this question? So I don't want to read the question out to you, right? Because part of physics is actually just reading the question properly. So I'll give you a minute to read it yourself and then think through your options. So again, it's annoying because it is a 1-mark question, but again, if you think about it, there's like 20 marks at the end of the paper. And last, if I quote me right, you have to, right now the grade boundary is 67% to get an A star. So if you can just get all your multiple choices right, you're basically sitting on a DC. Multiple choice questions are out of, normally 18 of them, aren't they? 8 to 30. Normally it's 8 to 30, which was that, or 8 to 27. Gosh, I can't do mental math today. 19 marks. So 19. So 19 divided by, the paper is normally out of 5. So if you get all your multiple choice questions right, you're sitting on like 22%. And multiple choice are nice, right? So what do we think? This went up slightly from last year. Okay, so hopefully you're thinking, we read the question now, it says we got using a charged electron and proton, so we're given the charge them, we're given the mass of them. It says which of the following statements is not true, okay? They put it in bold and they'll do that in AQA to make sure that you've read the not, okay? So what are we thinking? Can anyone pop in the chat what one is not true? So J and B says it has to be D that's not true. Do we agree? Do we disagree? So we're saying D is not true. Nalia, I haven't seen you yet. Yeah, thank you for trying and giving us a go because you're 100% right too. Yes, J and B, and that's the reason why. Good job, because it's supposed to be a uniform field. Nice. Yeah, perfect. Good job. So hopefully what we're seeing here, the first one says the electric field is uniform and points downwards, right? Clearly that is true because that's what we learned. Because electric field lines show the direction that a positive test charge move. It move away from the positive down to the negative. So we know we've got uniform field between these plates. That's true. Number B says the electric field strength is 1,330. Hopefully we had to go with that. So electric field strength, okay, is force per unit charge. So, or you could do electric field strength is V over D. So we were told the potential difference between the plates was 20. And we were told the distance between the plates is 1.5 centimeters. So 1.5 times 10 to the negative 2. And we do that math, I did it a second ago. I got 1,333.3 recurring, which to 3 significant figures is 1,330. So that one was also true. This one, an electric field plays in the field acceleration of 2.3. Hopefully you're thinking F equals ma. So if I want to find the acceleration, I need to know what force is on it. So remember, electric field strength is force per unit charge. So to find the force, I do the electric field strength times the charge equals the mass times the acceleration. The electric field strength we find here, so 1,330 times the charge, 1.6 times 10 to the negative 19, equals the mass, which we were told up there is 9.11 times 10 to the minus 31 times by A. So if we solve that for A, which I did a hot second ago, you get exactly 2.34 times 10 to the power 14. So it's the same numbers there, and it makes sense. If it's an electron here, it will go upwards because it'll be attracted towards that positive plate. So true. So exactly what J and B and Nalia said then. The only one that's not true is D, because it said the field is stronger and points closer to the plates. It's not exactly what J and B said. It's uniform everywhere. Okay, so even if you didn't do the math for B and C, hopefully straight away you noticed D has to be the one that's wrong. Okay. Right, next one. At X, which direction is the electric field pointing? Is it A, B, or C? Pop your answer in the chat. At X, what direction is the electric field pointing? So Soham says C. Carl says C. What do you think? Can I give you a hint? You're thinking about vectors. Omar says C. So it's not C actually, because of vectors. So for example, yeah, thank you, it is A. Yeah, it's A, right? Because if you think about vectors, do you know when you kick a football, that would be the force you put in the football? If you kick the football with much harder force, you would show that vector. So if we did the resultant force of this, you add them together. Or for example, if I had a force going this way and I had a force going this way, the resultant force between those is still a force going that direction. So hopefully what we're thinking about is that inverse square law, right? So remember, force is 1 over 4 pi epsilon naught Q1 Q2 over R squared. So if I look at point X here, it is much closer in distance to that negative side. So that force, because it's inversely proportional to the square, there's going to be a massive force here accelerating that positive test charge. Because remember, the electric field shows the way that positive would move. A massive force pulling towards that negative. Whereas here, the distance between these two is really, really high. So we've made that R really large. So the force there is much, much smaller. So the force is much smaller. So hopefully we can see, if you look at these two vectors, the resultant force on X will be going towards the left. So X didn't tell you what X was, but we know that electric fields shows the way that a positive test charge move, right? So that's why we're saying if it was a positive test charge, it would move towards the negative. Yeah, so we're assuming, yeah, we assume it, yeah, thank you, JMB. Because remember, just because of the definition, electric field strength is the force per positive test charge. Yeah, grand. Okay, next one then is to get you to do a bit of math now. So it says, number 3, calculate the electrostatic force on the electron in the diagram to the right due to a helium nucleus. So that's your first thing you need to think about. I've given you what epsilon naught is. I've given you the charges of a proton and electron, given the mass of electron and the mass of nucleus. And the equation you need to find force is 1 over 4 pi that you get given your data sheet, epsilon naught, Q1, Q2, over the distance between them squared. So have a go. What is that force? What is that force? Just want to see if you can practice using the equation. So again, what we're trying to find out is what is the force on this electron. So we know this is a positive charge, it's a negative, so there will be some force trying to pull it in towards a circle. It makes sense because the electrons orbit the nucleus, that's why it's circular motion. So I want to know what is the magnitude of that force on that electron. So see if you can calculate what the magnitude of the force is on that electron. So if you're thinking 1 over 4 times pi times 8.85 times 10 to negative 12 multiplied by charge 1, so it's electron, 1.6 times 10 to the negative 19 multiplied by charge 2 divided by the distance between them squared. So just try and see if you can plug in the numbers. So it's A, B, C, D, or none. A, B, C, D, or none. Talish says it's 1.84 times the negative 7, which you're saying C. Do we agree with C? What do you think? Yes, she's right. No, she's wrong. Are we struggling popping that much numbers in our calculator? So hopefully to give you a hint, a helium nucleus, hopefully we know this from particle physics. Helium nucleus is an alpha particle, right? 4-2. So what that means is it's made of 2 protons and 2 neutrons. So the charge, the second charge I have to use here, and I've got a picture here to help you out, was charge of 2 protons, which is 2 times 1.6 times 10 to the negative 19. The distance between them, hopefully we saw it was nanometers. So if you remember, that's 0.05 times 10 to the negative 9. And then we had to square that number, okay? So things that people always get confused here is they probably forget that it's 2 times the charge of a proton, and they forget to square the radius at the bottom. Yeah, see, Emma, Fab, Emma, Frank, and Talisha, you're perfect. So that's 100% right. Yeah, Nalia, perfect. Yeah, good job. So it comes out, your final answer as number C. So So 1 over 4 pi epsilon naught multiplied by 1.6 times 10 to the negative 19, technically squared, times 2 over 0.05 times 10 to the negative 9 squared. So that's the force of that nucleus is in that electron. Yeah, nice. Okay, next one. So two charged particles are exerting a force of 20 newtons on each other. So two particles, they've got a force of 20 newtons on each other. 20 newtons because Newton's third law. One of the charges is doubled and the other is tripled. So what we're doing is we're multiplying that charge by 2, tripling this charge, and the distance is halved. So we're halving the distance. So times 2 times 3, and we halved the distance. What is the new force on them? See if you can get it. Remember, the equation is F equals 1 over 4 pi epsilon naught Q1, Q2 over the distance between them squared. So what's going to be the new force on them? Pop in the chat. Is it A, B, C, or D, or none of them? Electrostatic force of attraction. Electrostatic force of attraction. Okay, so pop in the chat when you think you have it. No worries. Pop in the chat when you think you have it. So hopefully you're thinking, one charge it told us is doubled, one charge it told us is tripled, and the distance here is divided by 2. So the R divided by 2, but it's all squared mind. So Carl says it's going to be C. Do we agree? Omar says C. Do we agree? JMB says C. If I told you I didn't get C. And if you're getting C, you're probably just forgetting that when you divide it by 2, remember it's squared. Right, so what I would do here is F equals, that's a constant, so we're just going to ignore it, right? So what we've done is we've done Q has been multiplied by 2, Q2 has been multiplied by 3, and then what we've done is divide it by R over 2 all squared. So what we've done here is 6Q divided by R over 2 all squared, which means 6Q divided by R squared over 4. Remember, the same thing as divided means multiplying. So we've got 6Q multiplied by 4 over R squared, which means we have 24Q over R squared. So yeah, yes, brilliant. So we see that what we've done here, we've multiplied the whole thing by 24. So if it used to be 20, we have to multiply by 24. Yeah, fab, Talish, lovely. Yeah, Omar, Zila, JMB, Zila, Zila, how do you say it? Go and type your name in phonetically so I don't start saying it wrong. Yeah, so fab, that's going to be option D, 480 newtons. Yeah, nice. These ones, again, come up loads in that 1 mark part of the paper. And again, it's the problem is here that everyone forgets that it's R squared. So you divide by 2 is squared. Sheila? Is that right, Sheila? So it's R squared. Okay, nice. Okay, next one then, again, is getting you to practice. Sheila, oh, happy days. Thank you. Okay, the next one then is to get you to practice the math. So it says calculate the force of Q1 on Q2 and give the direction. So here's Q1, here's Q2. You pop in the chat, what is the force of Q1 on Q2? I've given you the information here. And remember the equation we're learning right now is F is 1 over 4 pi epsilon naught Q1, Q2 over R squared. And we also learned electric field strength is force per unit charge. And it's the same thing as voltage per distance. Okay, so it's the free equation we've done. So what is the force, just taking time, what is the force of Q1 on Q2 and give the direction? So what force is Q1 exerting on Q2? And what direction is it going? I've given you the charges down here, and I've given you the distance here. So pop in the chat. So hopefully you're thinking 1 over 4 pi times epsilon naught that I didn't give you, so sorry, 8.85 times 10 to the negative 12 times Q1, 0.5, Q2, 0.5. Distance between them is 10 nanometers squared. So what'd you get? 10 nanometers squared. This was nice because you didn't have to worry about, you didn't actually have to use the mass of the electron or the charge of electron, and just put it there so you had it. So what's the size of the number, magnitude, and direction? Okay, so hopefully then we popped it in our calculators. I got, did I get it? When did I do it? 2.25 times 10 to the power of 25. Yes, JMB, lovely. 2.25 times 10 to the power of 25. And then what's the direction? Is it right or left? Up or down? So what's that direction? Yeah, here, brilliant. Priscilla, lovely. I haven't seen your name yet. Yes, lovely. And what direction is it though? Someone be brave and give it a first go. What's the force of Q1 on Q2? What direction? Yes, Kai, nice, to the right, good job. Yes, Carl, thank you for putting a plus in, because we can see opposites repel, so Q2 is going to be moving towards the right, so that's towards the right. Nice, towards the right. Sorry, you went out there for a little bit, but I think we're back now. So what's the force of Q3 on Q2? So again, hope you're thinking F is 1 over 4 pi epsilon naught. Q1 this time is we're using 0.5 again. Q2 this time is again 0.5. And then R, the distance between this time is 4 nanometers. So the only thing we're substituting in here, instead of 10 times 10 to the negative 9, we're going to use 4 times 10 to the negative 9 all squared. So that's the only thing we've changed there. So what force do you get and what direction is it going? Yeah, 1.4 times 10 to the power 26 is perfect, lovely. So 1.4 times 10, exactly what I got, to the power 26. And what directions? It's going to the left. Do you sure? You sure it's going to the left? So remember, I want to know the force that Q3 exerts on Q2. Yep. A here, is hopefully I'm saying your name right. A here, perfect. So what force does Q3 exert on Q2? Yeah, Priscilla, good job. It's going to go to the right. Because remember, opposites attract. So Q3 is going to be attracted with much less number, but still going to attract it towards the left. Nice, so both of them is going to go towards the left. I drew right and I said left. Priscilla, you're right, sorry. I don't know, I drew it and I said left. I'm actually shocking at my right and lefts. When I did my driving test, when I was like, obviously a while ago, I had it right left. Sorry. I think I just buffered there a little bit. I'm back now. Yes? Yes, sorry. Okay, so then for this one, the resultant force of Q2, hopefully you're just seeing that you're just going to add them together. So all we have to do is add these two together because clearly they go in the same direction. So we add them together, we get a final answer of 1.63 times 10 to the power 26 to the right. Yeah? Okay, this one, so it's a quick one. What's the electric field strength midway between the two electrons? And explain your answer, pop in the chat. What's the electric field strength, the midpoint between the two electrons, and pop your answer in the chat. Yeah, 0. Yeah, good job, easy. Because remember we said a positive test charge here is going to be attracted, 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 attracted. But then the two negative charges, because we're going to get attracted to this one, attracted to this one, it's going to get attracted to this one, attracted to this one. So hopefully you can start to see in the middle here, there's a region where they're right in the middle of them, where the electric field is going to be 0, right in the middle, because they're going to be equal forces of attraction going in opposite directions. Yeah, Kai, perfect answer. Lovely, beautiful. Okay, next one then, so we're building, okay, so we're getting a little bit harder. So this is coming back to kind of like paper 1 when you had to do resolving forces, okay? So there's just, I want to see how we're doing here. So first thing says, we have our negative 45 microcoulomb charge, and it says it's in equilibrium. Draw a free body diagram for the forces on it. okay? And I told you what the mass of the ball is. So just because we're all together, but hopefully you're thinking there's a string there, and from paper 1, I know there has to be a tension there. And then hopefully you're thinking it's got a mass, so there has to be a weight pulling it down, so W equals mg. And we know we've got a negative charge here and a positive charge here, so we know that opposites attract, so we're getting some force going towards the right due to that electric field strength. So that's my free body diagram, okay? So I've kind of sketched there for you. Can you now write me an equation to balance the vertical forces and pop in the chat? What would be an equation to balance the vertical forces? So hopefully you're thinking we have to resolve T. So pop in the chat when you have one. What's an equation to balance our vertical forces? T sine theta is mg. Do we all agree with that? T sine theta is mg. Okay, so hopefully you're thinking there's theta. So there is my next theta. So yes, here, thank you. Yeah, Kai. Yeah, it's cos theta. So I don't know how you guys learned it in school, but if you do trig every time you do this, it's going to take up ages of your time, right? The way I do it is if you take your vector and you go through the angle, hopefully you see me do this TikTok. If you take the vector and you go through the angle, that's always going to be cosine. That's T cosine theta. But if you take your vector and you didn't go through the angle, so here I didn't go through the angle. Because I didn't go through the angle, I committed a sin, right? A sin. So if you don't go with God, so if I don't go with God, but I go against him, I commit a sin. So if you don't go through the angle, it's a sin. So that one's T sine theta. Yeah? So what we're saying here is T cosine theta equals mg. Because God is an angle. Well, that's where the angels are, but it's spelled wrong, right? Okay, what's an equation to balance the horizontal forces then? So now we just said T cos theta equals mg. Hopefully then we're thinking T sine theta is going to equal this force, okay? Now we know that force is going to be the electrostatic force of attraction, which is 1 over, yeah, thank you, Jimmy, 1 over 4 pi epsilon naught. I'm just going to write epsilon naught here because I'm going to do some math, is 8.85 times 10 to the negative 12 times by Q1, which you're given in this diagram, times by Q2, which you're given in this diagram, times by the separation between them, which you're given in the diagram, squared. Okay? So first thing can you quickly solve what mg is as a number? And can you quickly solve what that force is as a number before we move on? So in the chat, first thing I want you to do is tell me what is mg? And once you find what mg is, can you also solve what this number is in the chat? So I want to simplify this. T cos theta equals what number? T sine theta equals what number? And once you've done that, can you figure out then how do we get theta once we have that? mg is 0.49. Did I get 0.49? I did get 0.49, thank you, lovely. So 0.49, yeah, because all we have to do is the mass we were given is 0.05 times by 9.81. Yep, lovely, 0.49. So we're going to simplify this now. So I've got T cosine theta equals 0.49. What does T sine theta equal? What does T sine theta equal? So hopefully you're thinking Q1. Yeah, Kai, that's what you do. Yes, lovely. Keep going, see if you can get the final answer there for theta then. So first thing you got to do is solve this. Yeah, Ty, good job. Kai, perfect, that's what you do. So hopefully you're thinking I'm going to do 1 over 4 pi epsilon naught. So to write epsilon naught, we're doing 8.85 times 10 to the negative 12. Instead of doing Q1, hopefully we're thinking I got to use 0.45 times 10 to the negative 6. Instead of writing Q2, I have to multiply by 0.1 times 10 to the negative 0.012 is exactly what I got. Good job. Yeah, fab. 0.012. I got 125 though, so I don't know if you could write 12 or 13. Did you get 0.012 or 0.0125? Unless it was 4. Yeah, it's probably just 1. Yeah. Okay, so now we know t sine theta is 0.0125. Yeah, thank you, Emma. 1248. So I want to see why that's not 0.012. It's not. Oh, well, fair. Actually, fair. Yeah, if you were, fair. I get why you did that. Yep, fair. She's right. You didn't have, if you don't only do it to 3 decimal places. Yeah, you're right, 100%. Let's go that. Okay, so I know t cosine theta and I know t sine theta. How do we use these two equations to just find what theta is? So Kai, can I give you the hint up there? You said you divide them. Why would you divide them? What do we get if we divide them? So t sine theta. Yes, JMB, good job. Tan theta, yes, good job. T sine theta is 0.012. And if I divide that by t cosine theta, which equals 0.49, t is the cancel. Sine theta over cosine theta is tan theta. So tan theta is 0.012 divided by 0.49. So then to find theta, I just need to do shift tan in my calculator, or inverse tan, 0.012 over 0.49 to find out what that theta actually is. Yep. Michael, yep, fab, good job. Tan, so sine theta over cosine theta is tan theta. So what do we get then as our angle? 13. You got 13. I didn't get 13. Sorry, I was writing fab in the chat because I saw I was buffering there. But yes, perfect. Okay, so now we find theta. Can you now tell me what t is? So last step is just tell what t is. So what's t then? So hopefully you're thinking, now that I know theta, I can just choose to plug theta into either one of those equations. It doesn't matter which one. And then rearrange to find t. Yeah, Priscilla, nice. Michaela, nice. So I would probably plug it into the top one. I don't know why, I just like it. So t cosine of 1.46 must equal 0.49. So now I'm trying to find what t is. So t must be 0.49 divided by cosine of 1.46. Yeah, 0.49. Yes, awesome, thank you. So tension is... Yeah, awesome. Yeah, grand. Yep, lovely, 0.49. Yeah, triple check. Okay, hopefully you're thinking, that's actually like a load of math in one go, right? Because you're kind of paper 2, you're kind of like combining the stuff you learn in year 13 to the stuff you learn in year 12, right? So it is a lot in one go. But if you look at the math, it's quite impressive that, I don't know, but I was your age, I felt great when you saw that math in your paper, especially when someone who doesn't do physics looks at the math in your paper, they're like, what did you just do there? So good on yous. Okay, so we have what, 7 minutes left? Will we try the next one? Okay, so last question, we're flying through today. So hopefully you can see this was a past paper question. So was the last one actually. So this is the past paper question. And the first thing we want to do then is see, no, there's no multiple choice. That last question, this one, they're not multiple choice. Okay, this one. So show that the electrostatic force on the sphere is given by this equation. Lilac, if you just came to us, it's going to be a bit overwhelming if you just joined us. Okay, so hopefully you're thinking here, I know that there's going to be forces on this. I've got tension in my rope. I've got W equals mg, trying to pull it down because it told me what its mass was. And hopefully you're figuring out here, if it's pulled slightly towards the negative, it's attracted towards the negative, it must be a positive charge. It must be a positive charge because it's attracted towards that negative side there. Okay, so what you're trying to show me here is how do you write an equation for F? So how did I get mg times tan 6? So hopefully you're thinking, I need to resolve tension into horizontal and its vertical components. If that's 6 there, there's my Z shape. So in there must be the 6. So remember, if we go through the angle, we went, it's cosine, t cosine 6. If we didn't go through the angle, we didn't go with God, we went against God, we committed a sin. That one's t sine of 6. So hopefully what we're doing right now is we're doing t sine of 6 equals that force due to the electric field, and t cosine of 6 equals mg. And then this one is, remember like physics, they kind of repeat the same math quite a lot. Hopefully you're thinking I just divide them. So I do t sine of 6, which is f, divided by t cosine of 6, which is mg. My t's cancel, and I get tan of 6 equals f over mg. But I want to write it with f equals. So f equals mg tan of 6. Okay, so this was basically the exact same math as before. Okay, so then B and C are quite related. So you've got to do B first before you can do C. What is the electric field strength between those plates? Your grand. I like you're using grand. Okay, so remember I've told you the voltage between the plates is 4,200. Can you quickly, and I've told you the distance between the plates is 60 millimeters. Remember we've got 3 equations today. Electric field strength is force per unit charge, which equals voltage divided by distance. And we know that force equals 1 over 4 pi epsilon naught Q1 Q2 over R squared. So first thing you've got to do is find what the electric field is, and then once you have the electric field, can you find out what the charge is? So give it a go. So first thing you're doing is popping in what that electric field is. So hopefully you're thinking the easier equation there is V over D. Nope, I didn't get that. I don't know how you got that number, Kai, so maybe just write down what you did so I can help you out. So electric field strength is V over D, so hopefully you're thinking the potential difference we were told was 4,200. Divided by the distance is 60 millimeters, so 6 times 10 to the negative 3. So what do you get? No, Kai, I still didn't get that. Is that your final answer for the charge or for the electric field? Yeah, Omar, yeah, good job. It's going to be 70,000 newtons per coulomb or volts per meter. Yeah, nice, 70,000. Okay, so yeah, 70k, beautiful. So we know that F equals mg tan 6. We already know what mass is. We were told that's 22 grams. We know what G is. How can we use our answer there for E to find out what the charge is? What do we substitute in? Oh, you don't, yes, okay, so that's what this other questions worded differently. A lot of people want to calculate the forces first, doing this way, but you don't need to. E equals VQ. Energy equals VQ. How do you relate that to? So remember this E stands for electric field strength. So we just find electric field strength. Yeah, so that's where you have to be careful. So that's a weird one. Capital E is energy and capital E is electric field strength. Yeah, Ikira, I want to use that one. So electric field strength is force per unit charge. So what I can write now, instead of writing force, I can write electric field strength times charge equals mg tan 6. So what we have now is 70,000 times by the charge equals the mass, which is 22 grams. So remember, it has to be in kilograms. Times by G, 9.81, times by tan of 6. So just now you solve now for what Q is. So hopefully we're plugging in right now. We multiply all this out and then divide by 70,000. And I got, hopefully the same as you guys, you can give me a plus, you're probably still typing it in, 3.24 times 10, yes, Omar, beautiful, 3.34 times 10 to the negative 7 coulombs. Yep, here, beautiful. Nice, nice. Okay, so hopefully this summer school's got you well prepared for when this topic comes up this year. So, because this would be kind of nice if you see this come up and you'll be like, oh, this is grand, I know what to do, right? Because a lot of people forget in paper 2 that in paper 1 you did learn those rules about like sine theta over cosine theta is tan theta, and you still have to use them, right? It's not like you can just ignore the math that you've learned in paper 1 to start paper 2, right? So we had like a solid hour there of math, especially on a Friday. So I'm sure you're feeling pretty good that you got quite a bit of math done. You can like tap out now. But before you tap out, I just want to talk about the course that is happening. So just so you know, so this is summer school. So like you guys, it's great that it's free for you guys, right? Because it's like tuition is expensive. So especially if you were looking to pay for a tutor this summer, it's like 70 or 50 pound an hour. So that's what I just want to talk about. So next year, if you choose to do physics with us, I'll be the one that'll be teaching the year 13 spec. Okay, we do the whole year 13 spec after school. And how it works is the same as summer school. So you'll have lessons with me, then you'll have homework, and they'll have the solutions to the homework. So hopefully you've been having to play with that and having a look at how to get the solutions to the homework. And it's the reason that the company was set up and that all the teachers here want to work for it is because tutors are really expensive, right? And yeah, when I was a tutor too, and I was charging the same price as everybody else, right? Like, I wasn't a mug. So I was charging like 50, 60 quid for an hour tutoring, but the only kids I could tutor was kids who came from really wealthy families. And the kids that I taught that needed a tutor, I felt really bad for them, and I was always trying to give up extra time for them because I didn't want to recommend them to a really expensive tutor when I knew they were pupil premium kids. And it's not fair, right? So it is sad, right? So a tutor, if you're paying for that £70 an hour, the £60 an hour, say you do the £60 an hour tutor, over the whole year, that's costing your parents like nearly 5k, right? Which is mad. So what Maya Space has done is we're trying to figure out ways to make it much cheaper so that everyone can get access to tutors if you need it. So normally the price for a full subject for year 13 is around 810 to 1080, depending on what the subject is you choose. But because you guys are like trying to do summer school now and you're experiencing it, we're giving like a special offer off. So hopefully today you can see in the description under YouTube, there's a number for WhatsApp. And if you contact that, they'll give you the orange price instead. So like nearly half price off, okay? So if you work that out for over the whole lessons for the whole year, it basically works out like £5 or less per lesson. So rather than you asking your parents for 60 or £50 for a lesson, you're just asking for 6, right? And each lesson is twice a week. And then we also do a 14-day full refund guarantee. So say like you tell your parents you want to do it, you do it for a full week, and then you're like, holy, not for me. We do give the 14 days full refund. Okay, so it's something you could like try for a bit of experience. But hopefully because you're doing summer school, you already know what it would be like. And then there's obviously loads of other subjects if you didn't know about them. So I know physics, hopefully you guys love, right? Because a lot of people don't even have a physics teacher, or they don't like their physics teacher, which is really sad. And as much as I want to say that all the kids that I taught love me, I'm sure there was a few of them didn't as well. But there's also chemistry, who's taught by LaJoy and taught by Devinder. You've got English by Louis. You've got biology with Laura. You've got math with Dario for year 13. So you've got quite a lot of options if you want it, okay? There's also the Ultimate Pass, which basically gives you access to all the subjects, right? So you get access to all free year 13 subjects if you choose to do those subjects. And again, remember, just the discount code gets you like basically 50% off. It's 45% off right now. So it's up to you guys, but just so you can see, obviously I hope that you'll do physics with me, and that'll be the times that I do physics for year 13. When would it end? Do you mean this lesson today? It's over today if you're good to go. But if you mean like, do you mean like the course? So we start the second week of September, and then you'll do 2 lessons with me all year up until basically the week before your exams. So it's like a full year. So we would do, basically I've already planned it all. So we would do like September, October, November. September is kind of like a revision of year 12 stuff. And then we're going to do, because a lot of you have mocks, right? So September is going to be like a revision, like a quick catch up of year 12 stuff that's important. And going into, but I guess it depends if you did thermal physics or circular motion. So we're going to do like thermal physics and circular motion at simple harmonic motion, in September. And then we're moving on to like fields, so stuff we've been doing today. And then we're moving on to nuclear physics. And then at the end, we do like quite a lot of revision, so just loads of past paper questions on every topic from paper 1 and paper 2. So my lessons will always be on Tuesday and Friday. So do you have any questions about it? OCRA. So the OCR spec, the only time it matters about the difference is when it comes up before your exams, right? Because the OCR spec, the AQA spec, the Pearson, the EdXL spec, it's all the same stuff you cover, right? Everyone covers the exact same stuff. The AQA one's just a bit more specific on the definitions, but if you get the AQA definitions right, you'll not get it marked wrong, your OCR spec. The only time it would matter would be right before the exams. So you know how I would tell right now, I'd be like, oh, we're learning paper 2 stuff today. You still have to know that stuff for OCR, but it might not be on paper 2. It might be on paper 1 for OCR, right? So if you choose to do it, like, or if you want to send us a message. So hopefully you've been watching the TikToks. So actually, just speaking of that, if you like and subscribe, right, I'm going to start doing, or please do like and subscribe my videos, or give me a thumbs up here on YouTube. But I'm going to start posting like some videos on YouTube of tutorials. So I've already just got one up there on particles. And then on TikTok as well, I'll always be doing past paper questions. So if you've seen us on TikTok, I just do a past paper question, then I go for the answer, past paper question, then go for the answer. Like, that's still available to all you guys. So if you have a question about OCR to me in particular, you can just message me there on TikTok, and I can show you the cross links between the two as well. But if you have any more questions, please shoot. If not, enjoy your Friday and you're free to go. You're so welcome. Thank you. Thank you for joining today. I think your next lesson is Tuesday, isn't it? Tuesday, Thursday. JMB, you're so welcome. Thank you for being very active in the chat. Vasilia, thank you. Omar, same thing. Have a lovely day. It's Friday. Have a day, right? Ishaq, thank you. Nalia, thank you. Enjoy your day. You're so welcome. Have a lovely day. Yeah, thank you, Garrick. Appreciate you too. Okay, so if there's no more questions, I'll just tap out then. I think we're good. Okay, well, have a lovely Friday then. See you later.